critical thinking, logic, and algorithms. So you need to know the data structures and also the algorithm to solve the problem. The problem are mostly hard to solve by humans directly. They need some algorithm tricks, like some very complex algorithm to solve the problem. Like the third challenge for competitive programming is that when you develop the algorithm, you need also implement the algorithm with code. Like you need to write the program and test if the program is correct. So for this challenge, you need to know the syntax and all the specific requirements, domain knowledge for the specific programming language. So these challenges make the competitive programming a very hard task. And because like AlphaCode is like the first novel and effective model in competitive programming right now. So after talking about the problem setup, we'll go to the we'll see what AlphaCode do. We'll take an overview of the AlphaCode. So here is an example solution from generated by the AlphaCode model. So the AlphaCode first reads the two phrases, which are two strings, which are which refers to lines 3 and 4 in the program, and then they use the from line 11 to line 18. The program is checking the two string if the two strings satisfy the specific requirements. And the 19 and 20 are the backspace, which are the operation defined in the problem definition. And the last three lines will just return the final results. So this is the solution of AlphaCode, and it's correct, and it's also very effective. So we'll first talk about some backgrounds of AlphaCode before we dig into the details of the model. So briefly speaking, AlphaCode is a pre-trained transformer-based language model, and it's pre-trained on GitHub code with standard language modeling objectives. So we'll first talk about the transformer. I believe most of you guys are familiar with transformer because it's so popular right now. So briefly speaking, a transformer has a encoder. It could have multiple encoders as a stack, and also multiple decoders as a stack. When you input a sequence into the encoder, it will generate a sequence from the decoder. And what's inside the encoder and decoder in transformer is they have the key part is the self-attention. So the transformer uses self-attention to compute attention among all the input tokens, and it computes the self-attention with the key. They compute the values and use a feed-forward network to get update the embeddings, and different encoders could stack together for more rich, more informative embeddings. And after the encoder, the attention and the high dimensional embedding will go to the decoder, and the decoder will use the high dimension embedding to, and also the input to compute some generation probabilities. And based on the generation probabilities, the model could generate different tokens and sentences. And yeah, that's a brief introduction of transformer. And also like here's a reference which explains transformer in detail. I find it's really helpful to read. So if you guys are interested, you can refer to this link. It's a blog by Jay Adama. And also AlphaCode is a language model, and it's pre-trained with standard language modeling objectives. So some brief introduction of language model. So language model is basically a probability distribution or words or word sequence. In practice, a language model gives the probability of a certain word sequence being valid. So like the probability of a word is given the probability given the prior word, and we need to predict the next token. And generally speaking, language models could be categorized into statistical language models and also recently neural language models. The statistics models are usually traditional statistical n-gram models, also maybe HMM models, and like these n-gram models use some certain linguistic rules to like mimic the probability distribution of words and the human language. And recently, and I'll say like the most popular language model right now is the neural ones, and it's new and it has surpassed the statistical language models in their effectiveness. So there are different kinds of neural language models, include RNN, LSTM, and transformers. And yeah, after the background, so we'll talk about some details of the AlphaCode model. So we'll first talk about what data the model is using. So like I said, the model has two phases. The first is a pre-training. The second is a fine-tuning. So they have separate data for different phases. For the pre-training task, the data the DeepMind team use is some 100 gigabytes GitHub open source code. And the objective of the pre-training is to allow AlphaCode to learn code representations and solve easy explicit tasks. And for the fine-tuning stage, the DeepMind team developed a new dataset called Code Contest. It's a custom competitive programming dataset designed by the team, and the objective of the fine-tuning is to adapt the model to the target competitive programming domain. And so the Code Contest dataset is a compilation of problems, solutions, and test cases, and also the metadata. The metadata include the difficulty ratings and type tags from code forces, which is a code contest, and also description to code and connect. So here is the overall data used in the AlphaCode model. And for selecting the data, the DeepMind team actually found there are some problems with the original data collected. So the problem is the false positives and the slow positives. So false positives means some solutions in the training data of the problems are actually wrong, but since the test cases are only limited, they are tagged as correct in the training data. So this caused the false positive problem. And another exception is the slow positives, which are some solutions that are correct, but they are algorithmically inefficient. So they are very slow to execute. So they're correct, but they are not optimal. So these two problems cause the quality of the data to be very low, and so the DeepMind team think about a solution to address these two problems. So the team will try to generate some additional test cases by mutating existing ones. So the mutating includes randomly increment of decrementing integers, swiping or changing characters in strings. Like by these ways, they could generate more additional test cases, and they first verify these test cases by some correct solutions, and then can use these test cases to verify if the training data is correct, if it includes false positives or slow positives. So the results is pretty impressive. The simple solution actually reduced the false positive rates down to 4%, which is very important. So the data set after the verify process, the data set has a very high quality. So here are some statistics of the data set. So like the table on the left is the statistics of the code test data set. You can see it's divided into train, validate, and test size, and it has mostly 3 languages: C++, Python, and Java. And the top table is a breakdown of the GitHub data set they use to pre-train the model. It contains many more different programming languages, including those listed in the table. And actually, you can see the majority is still C++, which takes 40% of the data. And regarding the false positive, you can see in the table in the corner. So the code context is the data AlphaCode use, and without cleaning, the false positive rate is 62, but now it's only 4%. So the data cleaning process is very effective. And also compared to some existing data sets, they all suffer from the false positive problem. So yeah, I'll say code context is like the first high quality competitive programming data sets right now. Yeah. So after the collecting and cleaning the data, we'll talk about the specific model of the AlphaCode. So here's the overall structure of the model. So it's first pre-trained transformer-based language model on GitHub code with the standard language modeling objectives. And it then fine-tunes on the new code context data set using some different training objectives. We'll cover those in details later. So so this is the left is the training process. After the fine-tuning, the training process is done. So the right is the inference phase. So during the inference, the model will first generate a very large number of samples from the model. It's about usually about like 1 million samples, and then for those samples, they develop some filter and clustering process, which will filter the unqualified solutions and select the top 10 best solutions, which are going to be submitted to the programming contest and check the results. So the filtering, clustering, like the filtering is just like running the all the samples on the visible test cases, which are given in the problem description. And this step actually filters about 99% of the symbols. So after the filtering, there's only like 1,000 symbols left. And for those symbols, they just try to use some clustering technique to cluster those symbols. And they pick one solution from each cluster and submit the 10 solutions to the code contest. Regarding the size of the model, so the DeepMind team has tried different size of the model. Since you can use more encoders, more decoders, you can keep stacking the transformer modules, and you can get larger and larger models. So we can see the like the team actually found like shallow encoder and deep decoder significantly improve the efficiency of the training without hurting solve rate. So I guess it means the problem is more focusing on the generation part instead of the understanding part from the encoder. And the table shows some detailed configurations of the AlphaCode model. It has like the largest model has 41 billion parameters, while the smallest one has only like 300 million parameters. And one thing to notice is like this model can also be ensembled. So actually during the test time, the paper says when they try to assemble some of these models, the performance is even better than a single model. So yeah, here's some the configurations of the model. So next we'll talk about the detailed training process of the model. So the training has two phases. The first pre-training use standard cross entropy next token prediction loss and mask language model loss. So these two laws are used to pre-train the language model. So there are no labels involved in the pre-training phase. So it's a self-supervised pre-training, and the next token is just a common generation loss, which use the next token generation probability to the correct probability, which computes the cross entropy and use it as a loss. And for the masked language modeling loss, it's I guess it's first used in BERT, which is also a popular language model. So the idea is to mask some percentage of the input tokens and try to recover those masked tokens from the rest of the sentences. So like this, that's the loss for the pre-training. The fine-tuning phase is also, they also use the standard next token prediction, the masked language modeling loss. So, but since it's a more small domain and the authors also use the tempering and also value conditioning and prediction and code, which is it's a restriction to the loss function. So these are some techniques the authors use in the fine-tuning phase. So yeah, so here's the pre-training. So the first is the as I said before, there are two part of the loss function. The first is the standard cross entropy next token prediction loss. It's mostly for the decoder. So you can see in the red figure. So when you generate a token, you have some probability distribution, and you compute the cross entropy of this distribution to the real distribution, and you can compute the cross entropy loss. And for each token, you can compute the cross-entry loss, and you just like take a sum of all the losses and use them as the loss function. So it's a very common to train a decoder and also language models. And like a technique called teacher forcing is always used in training seek-to-seek models. And also the second loss is the mask language modeling loss for the encoder. As I said, is used in BERT. And the idea is to give an input sequence. We try to mask some of the tokens, and we put a mask token in the blank, and we feed all the sequence into the BERT and ask BERT to recover the original sequence, and we use the difference of the original sequence and the generated sequence as the mask language modeling loss. So these are two losses in the pre-training phase. And also here are two references I find useful. If you are interested in language modeling or BERT, you can check those references. So after pre-training, the model use some additional techniques in the fine-tune phase other than the two losses I talked earlier. So the model used tempering, which is a regularization technique that makes the token probability distribution smoother or sharper at training time by dividing the output losses of a model by a scalar temperature T before the softmax layer. So it's very simple but effective. So you just like divide the losses by a temperature, and it will force the loss curve to be smoother or sharper, and it sometimes gets better result. And also another technique AlphaCode uses the value conditioning and prediction. So the idea is pretty simple. So it tries to discriminate correct and incorrect problem summations as additional training signal. So it's like other than the two losses, it defines a new supervision for the model, which try to contrast the right and wrong answers for the same problem. So in this way, it helps the model to learn which solution is correct and wrong, and it helps the model learn how to generate correct solutions. And also the third technique is in fine-tune is called GOAD. It's an offline reinforcement learning algorithm, which allows the model to both learn from tokens it already assigns high likelihood, and also to ignore tokens that are not in its distribution. So since it's an offline model, so it's easy to implement, and the author find it's very effective in the fine-tune phase of AlphaCode. So here we can see here is the example from the AlphaCode during the training phase. So the left is what included in the training data. So it has the rating text languages. So these are the metadata, and it also has the problem description, and also the input output, and some example test cases, and the red is the correct solution generated by the AlphaCode. So yeah, here's just an example to show how the training and how the model is working.
I have a question about the input representation. As you can see, there are different parts in the problem description, such as the problem itself and the input description and output format, such as this. So to represent the input, does the model differentiate these different parts in the inputs?
Oh yeah, so like a common way to when you input some sequence into language models is to use a separate token. It's like it's just the separate token. You can use the token to separate different sections. Also, like I guess it's simple. It's just like put token between the metadata and the problem description. And in that way, the transformer-based models will learn these two are different parts, so it will have different attention.
Oh, I see. Thank you.
Okay, sure. Yeah.
Hi, I also have a little question about input and output. So I think I'm not fully understanding. Like in the paper, it says like it has like some kind of like estimation of input and output. So here in the question, we only have like one set of input and output. So I'm wondering like, it's like whole training process only contains like one input and output, or they have multiple one which generates by the model itself.
Oh, so like for the training, I believe you mean the fine-tuning phase, right? So for this code context data, the authors collect the data in a way such that each problem could have multiple solutions. So in the training data, one problem could have multiple solutions, and it could also have some solutions that are wrong. So also like the solutions are in different languages. So there could be a Python solution and also a C++ solution. So that's how they collect the training data.
Oh, I got it. Thank you. And for the for the question itself, like for the problem itself, is giving a set of input and asking us to giving a set of output. So I'm wondering, like in the training process, would like the transformer and like this fine tuning process take like the input and output from the problem into account?
Oh yeah, so everything on this on the left is input into the transformer model. So like it includes all the like the natural language description and also the example input and output. So these are all
okay.
input into the model.
Yeah. Okay, got it. Thank you.
Sure. Yeah. Feel free to stop me anytime when you have any questions. So yeah. So we have talked about the training phase of the AlphaCode. We'll next go to the inference, which also is also like the test phase of the AlphaCode model. So as I said, the first step is sampling. So so during the inference, when given a problem, the AlphaCode model will first generate about 1 million simple solutions. Like all these symbols could be candidate solution to the problem, and those symbols are generated half in Python and half in C++. And during the sampling, the metadata, like remember, like during the training, we input some metadata, like the ratings and tags, and during inference, they are not given. So the authors claim they just like randomize the problem tags and ratings, in the natural language problems. So the generated solution could be very diverse. It could be in different different programming languages, and also it could have different algorithms as text. And they also claim they use a relative high sampling temperature. In that way, the symbols generated are more diverse and contains like various different solutions, possible solutions for the problem. So after sampling, we get about like 1 million candidate solutions. So we need to search and narrow down them to only 10 candidate solutions. So the authors designed the filtering and clustering phase to filter the correct solutions from the 1 million candidates. So filtering is pretty simple. It's only remember the problem also has some example input and outputs. So the filtering just pass those example input and outputs to the candidates and check if the output is correct, is the same as the example outputs. And this step is actually very effective. It removes approximately 99% of the model samples. So after this step, we only got like around 1,000 samples left. And the next step is to cluster those 1,000 model samples. So the idea is to generate some new test inputs from the for the problem. This is done with a separate model. Like the model is also used the pre-trained model from the GitHub this side, and they just fine-tune the model in some different ways. So the model is fine-tuned to generate different new test inputs for the problem. And so during inference, given a problem, we could the model will generate some new test inputs, and all those 1,000 model examples will be cluster based on the solutions they gave to the new test. And after clustering those model samples, they just select one from each cluster and use them as the final candidates, which they will submit to the coding contest. And here's an helpful visualization of the process of the test time process. So this is this is actually a screenshot from a YouTube video. The reference is here is from a postdoc. He made a video, so feel free to check the video. It's very helpful. So here's like the pipeline. So for the first stage, the model samples at a large scale. So it has a given problem. It has a mailing code scripts, and the filtering filters 99%. So we end up with about 1,000 code scripts. And clustering include two steps. First, you generate test inputs from the second model, and you use those generated test inputs and to cluster those 1,000 code scripts, and you pick one code script from each cluster and use those as the final solution. So here's the overall process of the inference of AlphaCode. So here next we talk about some evaluations and the experiments of the AlphaCode. So the first evaluation is on the code forces, which is a coding competition, and so the DeepMind team used AlphaCode to compete directly with human programmers, and they evaluate the performance of the model based on the average ranking in the competition. So they tried 10 competitions during 2021, and like I said, they use some ensemble models like the 41 billion and 9 billion ensembles, which achieve the best results. And actually, they rank about the top 28% of the participants that have entered at least one contest in the last 6 months. So that's actually pretty impressive. So the model itself could compete with human programmers. And the red is just some ranking analysis of the model. And the next is remember, for the code contest this site, we also have the validation and test sites. So next, the authors validate the model on the test sets of code contests. So the metric they use is %k and %k, which are the percentage of problem solved when we take k samples from the model for each problem. And also 10 and k means the percentage of problem solved when you only allow to submit 10 solutions to one problem for evaluation. So like the 10 and k is includes the filtering and the clustering process, and %k is mostly on the generation part of the model. So results, here are some results of 10 and k for the model. So the model can successfully solve 34.2% of problems in the validation side. So with 100,000 samples, they solve 31.8% of problems in the validation side, and 29.6% of problems in the test side. So these are rates for the models, and clearly the clustering is very effective in narrow down the samples and find the optimal solutions for the problem. And here is some other analysis on the code contest experiment. So the x-axis is the sample budget. So it measures how many samples you try to generate from the AlphaCode model, and the y-axis is the solve rate. So the conclusion here is like increasing the data size will improve the solve rate across all spectrum of sample budgets. So you can see different colors means different percent of the data set. So using the full data set always has the best performance. And here is the solve rate scale log linearly when increasing the number of samples both in the 10 at k and %k metrics. So it means increasing the number of samples, so generate more samples, always help for models of different scales. Like no matter how many parameters the model have, more samples always help. But they claim like it will saturate at some point. So also like a large sampling budget will also require a more effective clustering and filtering process. So it's like a trade-off for the model. And here is the breakdown of the effective of the data set. So the authors compare the model pre-trained on different data sets, and they find actually GitHub is the most effective data set for pre-training. So if you use no pre-training, the performance is really low. And if use only natural language or Python codes to pre-train, the performance is also not very not very satisfying for the model. And here is a build-up application for the model enhancements. So no enhancement means the basic model without any tricks. So so the application shows like all those parts are effective in some way to help benefit the performance. So like all the mask level model training loss, the temporary, the tags and the metadata, the text and rating, and the gold and clustering, these techniques, they're all helpful in the success of the AlphaCode model. And here shows the effectiveness of the filtering of the AlphaCode. So we can see clearly the example tests are really important in the AlphaCode model, and it helps filter out more than 99% of the model samples. So very, very effective. And next is the clustering analysis. So the red line is without any filtering. The solve rate is really low because we end up with too many samples. But with the filtering, we can see the performance boosts a lot, and with some clustering, the model also has some performance boosts compared to the green line. The blue line is the optimal, so it's the optimal value we could reach. So we can see both filtering and clustering helps. They almost reach the optimal value when the sample budget is small, but with larger sample budgets, there's still some distance for the model, for the clustering and the optimal. So here's the third experiments for AlphaCode. So it's trying to comparing the model to some previous AI coding systems. So the baseline is GPT-Neo and Codex. So there are like previous state-of-the-art models, and the results are shown in the table. So clearly, AlphaCode is much more effective compared to those two baselines, and even a 1 billion parameter model can easily outperform the GPT-Neo at all difficulty levels, and also outperform the Codex baseline. So it proves the effectiveness of the model. And
so in the previous slide, the Codex 12B is like 24.52% for introductory case, right?
Yeah.
But AlphaCode is a little bit less. Is there any reason why? And even in in like Codex 12b, where it says n/a with 1,000 attempts, it is like 25.02%. Is there any reason why it performs like this? And what is introductory, interview, and complete competition? Is it just the level of complexity, or does it also have any other meaning?
So yeah, so this experiment is done on a benchmark. It's like the apps. So the apps is not just competition coding design. It also has the some interview problems and the introductory problems. So like these three categories are just like the different category of the problems. So although AlphaCode, since AlphaCode is fine-tuned mostly focusing on computation coding, so I guess the its performance in introductory and also interview categories are actually weaker than in computation category.
Okay. Thank you.
Yeah, sure. So
sorry, I also have a question about the results for the solve rate, the one plot with the curves. So actually we can see like for at least for this one, for under 1,000 samples, we actually don't have like any single correct answers. So do you have any idea like how is the result like this? So if the correct answer generated from AlphaCode is just if there are enough permutation of the codes, there will be like a correct answer.
yeah, so I think remember when generating different samples, we try to randomize the problem tags, like those metadata. So we have different metadata which will get different samples. I guess with only 1,000 samples, like when you randomize the tags or the of the routines, you could enter some actually incorrect values. So in that way, the sample generated will only generate some wrong answers. So I guess the idea is when the sample size is large enough, the randomness actually works, which gives you some diversity in the generating samples. That the diversity will help find the correct answers.
I see. And also I have another question, probably that's in the paper, but I probably miss it, is that how do they pick the final 10 outputs after clustering, that if the clustered number is like more or less than 10 cluster?
They actually they only say if there are 10 clusters, they pick one from each cluster, and if there are less than 10 clusters, they repeat the process, like pick the second one from the first cluster. But they didn't say anything about like more than 10 clusters. So I guess normally the results are not that diverse. Like they normally end up with less than 10 clusters, I guess.
I see, but how do they decide like which clusters they are going to like pick one more? Do they have a rank?
They didn't say. I guess you can like maybe rank with the cluster size. That's just a guess from me. So I guess that's a one way to do it.
Oh, I see. Thank you.
Yeah, sure. Yeah, so we go back to the analysis. So the authors also analyzed the copying mechanism in the AlphaCode. So they claim AlphaCode is not simply copying from the training set. They validate their statement by computing the longest common substrings between correct validation problems and also the generated solutions. So we see the model generated solutions have a similar distribution of human solutions. So they claim the AlphaCode is not just like copying from its training data. And yeah, here's another example. So the left is the human written solution, and the left is the model generated solution, and the right is a human written solution in the training data side. So we can see AlphaCode copies some lines of code from the training data, but that only works on the input parsing part, but not the core algorithm part of the code. And also the authors also analyzed the model solution characteristics. So we gave some analysis in the appendix to compare the outputs. So they claim AlphaCode is better on Python compared to C++, maybe because C++ is harder in syntax, and it still generates some of that codes, but that's have a similar percentage as humans. And as model get larger, the models are better at solving problems across different types of tags, and obviously those models are better at solving problems with lower difficulty ratings, because the solutions will be simpler and easier for the model to get the correct solution. And they also analyze the sensitivity. So here is they test the outputs of the model, and they claim they try to add different noise to the model and see if the model can still generate the correct solutions. So from this sensitivity testing, they claim so the simplified description of the problem increased the solve rate, which means the natural language understanding part is still hard for the model, and also the solve rate goes down dramatically when given related but different problems. So it shows in the B in the table. So when you do some opposites or related or verbose version of the problem, the model can't really just tell the correct solutions, and it's hard for the model to generate solutions, and largely unaffected by changes that do not seem significant. So if you like replace some words or remove some tab details, the model can still generate correct solutions. But if you delete some words or make the problem ill-posted, the model will tend to fail to generate correct solutions. And also, they also found the model relies on different sections of the description. So separating sections actually works, and it specifically rely on the specification of the problem description. And for different tags, the models have some tag sensitivities. So the authors try like during inference, they try to use true tags, use random per problems, or use random per samples. Actually, they found sampling with random tags per sample is even better than using true problem tags. So they claim that's the performance improvement comes from the extra diversity of samples. So I guess that explains why using a large simple budget will help the solve rate. And also they also talk some of the limitations of model. So during training the model, they also found even when the validation loss starts to increase, the model still not overfitting, but since the test performance is still increasing, so they argue that the validation loss is not a perfect match for like pre-training the competitive programming models. So they argue maybe using some high correlated metric to decide when to stop training the model will end up with some better models, but better checkpoints, and could further increase the performance of the model. And yeah, here are some impacts of model. So some possible applications such as making existing programmers more productive, and like suggesting some extended code completions to optimize some codes, and some AI coding system could also remove entry barrier to some non-programmers. So there's some possible future applications, and here's some roadmap of the model by DeepMind. So you can see there are still a lot of space to improve compared to some top human competitors. So I guess that this means like the competitive programming is a really hard task, since AlphaCode like already beats top human athletes, but in this competitive programming, there's still a large margin. So it means the task is really hard, and we can still see some progress in future, I guess. And the authors also talk about some potential risks of the model, such as like interpretability, generalization, also bias, fairness, and the repetitions. So I guess the bias is a common risk in all language models, since the code generation models are prone to reproducing the bias and also unfairness from their training data. And also, since code generation could enable both threat actors and threat defenders, so it may also have some security issues. And since the model is extremely large, so like pre-training the model the compute for the for pre-training the model is very high, so it may have some environmental impacts. And also, since the model is pre-trained on GitHub, so the data license of the open source data may also cause some IP problems. And also like the automation problem. So if the model performs really well in code developing, so it may be decrease the demand for programmers, and that's hard for the job market. And also like the ultimate risk, which is the advanced AI risk. So coding capabilities could lead to a system that can evolve and recursively write and improve themselves. So maybe like the movie Matrix could come true someday, maybe. So yeah, so here are some conclusions for the paper. So AlphaCode is a SOTA system to code generation for competitive programming, and it could solve even unseen programming problems. So evaluation on code forces shows that AlphaCode could roughly perform at top levels of like median level of the competitors, and massive scaling up sampling and then filtering, clustering this is helpful in the competitive programming task. And AlphaCode is not directly copying from the pre-trained data. Instead, it's actually generating new solutions to so they can solve unseen problems. So, yep. And here are some references. So this is a blog about the paper. It's very detailed, and also this is a blog by AlphaCode. It's also introduced the paper, and also this is a video on YouTube by a postdoc, and he also explains the AlphaCode from high level. So they're also they're all helpful, and feel free to check those references. And also the AlphaCode, the DeepMind team also provides some visualization for the attention, also the results for the AlphaCode module. So it's on this link, so feel free to check. And a simple visualization shows like this. So given the problem, the model will generate solution. And when you move your mouse on the solutions, it will show the attention and the generate probabilities for each token. So that's also interesting. Feel free to play with it. So yeah, that's all my presentation today. Thanks.
Okay, so the presentation is pretty good, right? It covers many things for this paper. And also this paper seems to be different from what we expected for the AlphaCode. Before I have a very high expectation for this paper, but after reading this paper, it seems to be very different from what I think about this paper actually. Okay, so let's hear about the audience. And do we have any questions?
Yeah, I have a question about like the sampling, like mass sampling and then filtering that is applied here. So I mean, my understanding, like I'm not a competitive programmer, but like from my just like experience in with lead code, for example, I mean, the questions in the competitive programming, like in general, like the coding questions, these like algorithmic questions are not like extremely diverse, even though like I'm sure that all of them are different, but like they're quite similar to like each other in terms of like the methods. I don't think there is like more than like 1,000 methods. So like wouldn't generating like 1 million samples from like sampling like 1 million candidate solutions and then filtering all of them like manually would not be something like p hacking, for example, like because I mean then they like the biggest work goes to those like manual, for example, code executions and then test cases and everything, rather than what the like network's outputs and even the network outputs. And then even in that case, like the accuracy is like 20% in questions. So for example, it's almost impossible that with one sample, the code generates something that can solve the problem, like 0% chance almost practically. Wouldn't it be just like, I mean, doesn't it show that like the network is still like quite weak in terms of how to generate any kind of a useful solution to the questions, right?
Yeah, I totally agree. I also think the performance and impact of the AlphaCode is very limited, since the performance is not actually it's not that satisfying, and I guess it's because the task is difficult, but I guess it's still a long way from the real world application of AlphaCode in daily life, because I think the performance is like, remember, I think the DeepMind team has several projects like the AlphaGo. It beats the top athletes, and it has the AlphaFold, which they try to unfold a protein structure, and it's also very effective. But compared to those projects, I guess the performance of AlphaCode is quite limited, I assume. Yeah.
Thanks.
Yeah, any more questions?
Hi, Professor. I have a question about how this this system converts the natural language to a kind of logic, and then that's the first part I got confused, because mostly I think the model is how to generate the code and how to convert the natural language, the English language, to the logic and then convert to the code. And that's part I kind of lost. Could you please emphasize how, or briefly to show again how it works?
Yeah, sure. So it's not actually it's not like converting natural language to logical language, because
It's
so
sequence to sequence, right? It's not.
yeah. After all, it's a sequence to sequence model, so it takes in a sequence and it generates a sequence. That's all it do. So it does. So it's just like a sequence to sequence models. So and then, like, the input is just the input could be metadata, could be natural language, could be science or numbers. Like, they will all be converted to some embeddings, some vectors, and the model only takes in those tokens, those embeddings, and it actually like I said, it won't distinguish the tokens from language or from numbers too much. It's just like tokens for the model, and the whole input is just a sequence, and the whole output is just a sequence. So it's just a traditional sequence model. There's no like converting or something in there.
There is no logic generally. So it's a sequence, input is a sequence of words, output is also a sequence of words. They have no logic about the how to program is code, actually.
Oh, does that mean the designer has to pre-process these questions and make it sequential like this example? Then the model can convert to the matrix or vector and to generate code, right?
The input can be any can be just a document, right? Not as shown like here. Right? It can contain a sequence of words.
Yeah. The input could be in any format. They just use like for transformer-based models, they have a tool called tokenizer, which will build a vocabulary and try to tokenize each word into some high-dimensional embeddings. So that's how it's bought.
Okay. Yeah, I'm still confused, but I will double check the paper again. Thanks.
Yeah, you can check the transformer paper as well as the BERT paper for these two papers for more information how that works. And also you can also check the toolkit. It's called Hacking Face. They have toolkit for transformers. You can try to run the model as well to see how it works. Yeah.
Okay. Thank you.
Yeah. So any more questions from students?
I'm curious how, I mean, this is obviously a very difficult question, but for the presenter, I'm curious if you have any ideas on how a system like this could be made more efficient, or what is missing, I guess. I think Barris pointed out that just sampling, 1 million samples from this seek-to-seek model seems like a very brute force kind of approach to obtaining a solution. So I'm wondering if there are any kind of like human knowledge things that you could embed in the system that would make that search more efficient, or like not rely so heavily on brute force.
Yeah, I guess like I remember he said like for like problems on LeetCode, like they follow a specific format. But I think in this in the code context data set they build, the I guess the problem are more diverse compared to LeetCode. So maybe that's why the performance is not that high as I expected for AlphaCode. I guess that's one difference maybe.
Yeah. What like what jumps out at you as being missing from this architecture? Like I would think maybe some like symbolic or logical representation, maybe like the function signatures for the built-in functions for whatever language that you're using as like additional knowledge maybe could be used to augment the task, rather than having to learn all that stuff just through like kind of token correlations. But any other ideas on like what could be added to the system to make it less just kind of compute oriented or like brute force oriented?
I don't know. I guess like maybe one possible way to do that is to try to like distinguish natural language from logical forms in the tokenizer. I guess maybe building some separate tokenizers could help. I guess that's just one guess.
Yeah, that's interesting. Thanks.
Yeah, for this, I think, I mean, before, if we use transformer for translation from one language to another language, it seems its performance is okay, right? When it comes to this paper, I think generally don't do any learning, right? I mean, for the learning part, it seems to be very weak because I see the model comparison for the AlphaCode, I mean, with 9 billion and also 41 billion of parameters. It seems that the performance is very close, right?
Yeah.
I think the majority of the contribution seems to comes from the post-processing step, right?
The sampling and filtering, yeah.
Yeah, sampling, clustering, and filtering. This post-processing matters a lot for the performance. Generally, this sample, I mean, they try to use the transformer to generate a pool, right, of candidates. As for the quality of a pool, it seems to be very bad, right, because they filter 99%
exactly
of the scripts, right?
Yeah.
And they further use some other steps for post-processing. It seems the post-processing matters a lot for this method, right? And the learner part seems to be very weak for this method.
Yeah. Do you have any intuitions on what could be done to make the learning more efficient? Obviously, like they tried very hard to make it efficient and didn't, I mean, succeeded only to a limited extent, but does anything come to mind as like a future direction to make the learning more efficient?
Yeah, one idea in my mind, because the program is very, grammar is very strict, it's very fixed. So we can use some like parser or some syntax or the structure of the code, I mean, incorporate into the model when we do the generation step, right? It probably will help a lot for filtering many of the candidates in the very beginning. Also seems for the learning part, I mean, for the inputs, it seems to be very noisy, right? The input seems to, I mean, it covers so many diverse things there. We can also further cleaning the inputs, I mean, from the natural language inputs into a formal way, I mean, for as input for generation of code, right? I think it will help a lot because according to our experience in the translation from language to language, it seems transformer works well, right? But when we do the translation from natural language to program language, it's so bad, right? According to the performance. Right? There should be lots of opportunity in this direction. I mean, we can try for further improving, proposing some new methods instead.
Yeah, thank you.
Yeah, so any more questions from the students?
Yeah, so similar to the previous question, although the authors mentioned that, this model is specifically focused toward the competitive programming solutions, but I was wondering to make it more generalized, maybe for the development or something like that. Can we add more scores and track those metrics to, make the core more maybe modular or maybe more readable? So for example, if we can somehow add some modularity score and try to maximize the modularity and, so that way this model can be more generalized towards the development as well, as opposed to only for the competitive programming.
Yeah, I think it's a good idea, right? Yeah.
Yeah, that was my thought. Thank you.
Okay, thanks. Yeah. Yeah. Any more ideas or questions?
I have a question. So I think in the pre-training part, it just like fitted all the code from GitHub to the transformer like without any labeling, right? And just like it just fit it into the pre-training model. And I wonder like if we could like in that step add any label or any else to like foster the learning? Would that like would that be feasible, or would that?
Yeah, hoping you can help answer.
Yeah,
the
yeah.
question.
Can you repeat? Like, I didn't get the question. Sure.
So like in the pre-training part, I guess like in the paper it's just it didn't mention a lot. Like the pre-training part is only like fitted with the GitHub repositories and all the code like doing some selections, and without any further labeling or any other just like so do you think it might be a way that to add something inside the pre-training part and give that a sense like what the code is about? Or for example, like we know like React maybe a framework. So would that be a good way, like we add some labeling, like showing how the code is doing, right? To like to some kind of to like have a grasp on what the code is doing, and to have like further interpretation when it's come to computation level or any other task.
Yeah, so I guess the problem is like first pre-training, the pre-training data is 400 gigabytes. It's very large, and if you try to human labeling the data, it will be extremely expensive. I guess it's almost impossible. So for the pre-training, I guess almost large language models, they use like the pre-training process is more self-supervised, which requires no labels. I'm pretty sure have some labels will help, but that will be like barely possible to get for in real life. Like for the GitHub codes, you can't ask annotators to annotate those codes. That's too expensive. I guess adding human annotations will help, but it's just too expensive.
Okay, got it. Thank you.
Yeah, for this question, I think some idea maybe it depends on the code complexity. Right? For some easier code, like for sorting or some hashing or some ranking, like algorithm or method or functions, if we say this we add some like ranking or some term or some tags into the natural language description, then we could probably can help the code, I mean, to generate the style to be for ranking or for sorting or for other kind of specific functions, right? I think it will probably help. It really depends. I mean, for this concept, I mean, for the current model, probably it will not help much because it's just treated as a sequence to sequence, right? Then we probably need to change the architecture of the model instead to incorporate some more supervision information into the model architecture. It really depends on how we do this, right? Yeah, so I think the question is good, and more questions from students. I think currently this model is still far away from being deployed in the real world because its performance is not very good actually. So you have no worry about if this model will replace your job or not. It will not replace your job for the future. Right? So no worry about that. Okay, so I think this paper seems to be, I mean, the title is fancy. However, when we read the paper, we find many problems with the paper. Right? It's not perfect. It has many problems. However, at the same time, they can also provide us with some ideas for us to try in the future. If anyone in the class who are interested in deep learning combined with software engineering with program synthesis, you may consider in this direction to try to propose a new method for this code generation as well for your project. Yeah, so if you have any question or ideas, you can talk with the presenter or talk with me, I mean, during the office hours. So I just want to have any more questions for this talk, for this paper.
I have actually a question about generally about the structure of this class. Can we maybe I really enjoy the last part of the class, last part of the presentation where we ask questions and then we just collect some ideas about the questions. So can we make it a little longer? Because for example, for this one it was 15 minutes. Can we make it maybe half an hour, like the last half an hour would be just like a discussion on the paper, because we already write a review about the paper. So everyone has like a minimum understanding of the paper already before coming to the presentation. So we can just like get very valuable insights in the last like 30 minutes of the class, actually.
Yeah, we can do another way, because right now the plan is for 1 hour for presentation and probably 20 minutes for the discussion. Right? For the first 2 papers, the papers are very long. I mean, this one is about 70 pages. The previous one is about 40 pages. Right? And in the following papers, I mean, it will be shorter, probably 10 pages or slightly longer than 10 pages. Right? Then, I mean, I think for the following presentation, it will be shorter, and then we can have more time for discussions. Yeah.
All right.
Okay. All right, so if you have no questions, then probably that's it for today's class. And thank you a lot for your coming and your attention. And let's also thank the speaker for the presentation. Thanks.
Yeah, no problem. Yeah.
Thank you.
I have a question to you, Professor.
Yeah,
When
you
will
can ask.
when will the results be out for the first 2 reviews that we have done?
Can you say it again?
The reviews that we have done, there will be points for that, right? Like when will they be released?
Which one will be released? Can you say it again? I didn't hear you.
Okay, sorry.
The paper reviews.
The paper review, right?
Yeah.
You mean the grading for the paper review, right?
Yes, yes.
Yeah, the tier probably will have to grade the paper review reports. I mean, generally, if you submit and you write something, I mean, about the paper, I mean, precisely, then you should have no worry about that, right? We will grade that. Yeah.
Yeah, you don't have to worry about the review point, because I will basically grading on the review based on how many times you have submitted your review, and I will also look through one review. So this process may be finished during the midterm and before the final exam. No final exam, before the final. Yeah, so you don't have to worry about it.
Yeah, I think probably we can mark maybe for every week, right? If it is complete or incomplete for every week, right? Instead of waiting until the midterm or final exam state. We'll do that, maybe update the grade table every week. So we can just mark it is complete or incomplete instead. Can we do that? Sure.
Because our each review is marked as 0 points, so I don't think there's a way to tag this. Maybe I can add a comment. Yeah, because we just have 0 point for each review.
Yeah,
Maybe
it is 0 point, but it is, I mean, with choice is either complete or incomplete, right? You can check them, and then you can also provide them with some feedback, right?
Yeah. Because if one review is not marked as missing, I think this can be marked as complete. Yeah.
Yeah. Then we can update them. I mean, provide them with some feedback every week. Right? We can do that.
Okay. I can do this.
Yeah.
Mm-hmm.
So the reason why I asked it is because this is the first time, honestly, I'm doing this course, which is related with a lot of paper reviews. I don't know if I'm doing it in a right way or not. I would like to know about that. So that's why, if at least like the first week is reviewed, that would be very helpful.
Yeah. We can provide with some feedback. I mean, for the first week and also for the following week. Sure. So here the main motivation for the paper review is to push the student to read the paper before class, right? The main reason is because, I mean, if you don't read paper before class, then if you just attend the talk, you can get notes very easily. So please make sure you read papers before class, and also analyze the paper contents according to a review reports to make sure you understand the materials, right? Then you can attend the talk and not do discussion. Then you can learn something useful. Right? Otherwise, if you just attend talk without reading paper, then you can get notes very easily. Yeah.
Thank you, Professor. Have a good day. See you.
Well, you too. Yeah. Any more questions?
I have a question. So I have one logistical question and then one question that's a follow-up on the paper. The logistics question, I accidentally submitted my review for Wednesday in today's assignment. Can I email the TA maybe today's review and then submit the correct one on Wednesday? I accidentally submitted the self-driving one for today's paper review.
If I understand correctly, so you submit today's review to the Wednesday class link, right?
I accidentally submitted Wednesday's review to today's class link.
Oh,
So can I, like, is it possible to resubmit still, or maybe I can email the TA my submission for today?
yeah, you can talk with the TA instead, right, after class.
You can just email me. I can substitute your materials to the newer one.
Okay, awesome, thank you. And then on the topic of this paper, so in machine translation, I would imagine there's not so many like fluent translations of a given input. Like if I'm translating from English to Chinese, maybe there's only so many ways to express the English statement in a corresponding Chinese statement. But for code generation, it feels like there are many more ways maybe to code a particular solution, especially because dead code is not really affecting the correctness, but like there's not really such thing as dead language in like a machine translation. So I'm curious if anyone is aware of some work that has tried to capture like the diversity of valid outputs and how that correlates with the efficiency of sequence to sequence learning, or if anybody has any intuitions on how you would formalize that idea.
Okay, yeah, how about maybe you can provide him with some feedback for this.
I guess this work is different in this from translation in the sense like for translation there's more like a mapping between different language, like a word in Chinese could map to a word in English, but in this one there's no like this model is more about like generating. It's more like generate the algorithm and logic from scratch. So I guess that's why it requires the large sampling and in the sense I guess the large sampling also one reason for the large size sampling is also like for most of the generated codes, they are not runnable. I guess if you limit to, and it's I think it's extremely hard for model if you require it can generate syntax bug-free code. I guess that's impossible. So that's why this paper used the large size sample. But I guess from my experience, if you work on natural language generation, the sampling is not that useful, like for summarization or like just like text generation, you do not need a large sample size. Normally you just sample with 6 or 8. That's a
top
very
10 beam search or
small.
something with like nucleus sampling or something like that. Yeah, I agree. So the thing that you mentioned about there's not like a one-to-one token mapping, like you can name the variables arbitrarily basically, and it's not like a single token in the input that corresponds to any of the operators in the output. That makes sense for why it's a more difficult task than machine translation. Yeah, thank you.
Sure.
Yeah, okay, so any more questions? If you no question, then probably that's it for today's class, and thanks for your time.